Distinguished guest, respected management, fellow students and staff, delegates, ladies and gentlemen, it is an honor to stand before you today to welcome Dr. Muhammad Uddin, our keynote speaker for today's session. Dr. Muhammad Uddin is an associate professor in mechanical engineering at UNISA STEM in the University of South Australia. Dr. Uddin focuses on advanced manufacturing and surface engineering research, underpinning industry challenges. By leveraging strong collaborations and industry partnerships, Uddin has built significant research, leadership, and capacity in his field of research. Uddin has secured a research grant of more than $4 million from all 4 Australian competitive funding categories, including IMCRC, CRC, ARC. His recent major grants include universities, Trailblazer programs, iLunch grant of $2.8 million on additive manufacturing through EBM for Australia's Sovereign Space Capability 2022-26 with USQ, ANU, CSIRO, and QPE Pty Private Limited. Dr. Uddin's research impact and track record can be evident by his extensive publications, which is more than 80 in high-quality Q1 journals, growing H index of 27, and citation counts of more than 3,100. Dr. Uddin received BSc in Mechanical Engineering from Bangladesh University of Engineering and Technology in 2002. And also Masters from National University of Singapore in 2004 and PhD from University of Kyoto in 2007. Welcome you, sir.
Hello, good afternoon. And thank you, the chair. Can you hear me?
Yes, sir, we can hear you. You can start.
Okay, thank you. All right, good afternoon. And thanks for the nice introduction. And first of all, I'd like to thank the organizing committee for this conference, really to invite me to give a talk and share my research experience and some of our research work we have done recently. So I'm going to share my screen just in a minute. I hope you guys can see me now. See my slide? You guys can see my slide?
Yes, sir. Yes.
All right. Okay. Thank you. Okay. So today I'm going to talk about my research work and some of the advances in the prospects in the area of surface engineering. That's going to really help transform the manufacturing landscape. I guess while I'm working in Australia, but of course the approach can apply to anywhere in the world. So, and I'm working at University of South Australia. UNISA STEM is the unit I'm basically based in at this moment, and I am leading the Advanced Manufacturing and Surface Engineering Research Group at the unit here. So all right, so let's begin with the outline of my talk. So first of all, I'm going to give you a bit of kind of overview of the manufacturing landscape. What are the manufacturing areas? we should really underpin, and then challenges over there, and then why the surface engineering is very important to manufacturing. And then I'm going to take a brief kind of overview on the current approaches or strategy being used at this moment to address some of the manufacturing problem. And I'll give a few examples or case studies from my research groups. So some of the interesting findings, what we do in the area of surface engineering. And then briefly, I'm going to touch on some of the emerging process or strategies that are currently being used for future transformation of the manufacturing. All right, so I think just to give you a bit of Australian manufacturing landscape first. So because Australia is a industrialized, developed country, and so Australia has got a quite aggressive vision about the manufacturing, and the focus or the reason behind that kind of ambitious manufacturing process is basically to develop innovative and high value adding products that can extend the service life of the components or mechanical systems, right? So and also the next one is basically to create that is going to actually create the niche markets across the world. So that means the products developed by innovative manufacturing process or in Australia could create the new market, new products, right, across the world. And by doing that, also Australia is focusing on tremendous R&D effort. So this is very important to develop like a sustainable, innovative impact on the manufacturing area. So this is just a few examples on the figures you can see on the right side are a few areas of where the Australia has focused on tremendous manufacturing innovation. So starting with the mining, which is the one of the key areas, right? Really, Australia has focused on to develop technologies, machineries, and really to produce high quality minerals. And the next one is, of course, is the biomedical areas. So that means Australia has got a quite good reputation in terms of developing innovative biomedical technology or products that can address some of the emerging medical problems. So next one is, of course, in the area of the space is the growing area, like other countries, even in India or America and other European countries. So Australia is also putting its footprint into the space area, so launching the satellites. So there are a lot of innovative technologies that are going into this space area. So Australia has focused a lot into this area, how they can actually create their own sovereign capability into the space as well. Defense is another area. So the Australia has got its own independent defense capability. So and constantly really investing money and effort to develop the new technologies into the defense areas as well. So and some other areas like the renewable energy, like solar and windmills and other renewable energy, where Australia has focused on developing new technologies to improve the efficiency of the power generation to the renewable energy process here. So and these are the key areas of focus where the manufacturing has to be innovated, and then how we can do that. So that's the big question. So and I just like to give you a few examples of the manufacturing challenges. Um, and these are just few examples, but there are many areas we are actually focused on. But these are some of the areas where probably my research group has been quite focused on, and we have been working on this area for some time. So um, first one is basically the biomedical area. So developing the implant, so which is basically the magnesium alloys is being used as an implant material, is a biodegradable materials. So there is a great potential of using this particular material for implant. So it is the best good thing with this implant is basically once you put that implant into the body to fix the bone fracture. So this implant would be degraded over the time, and then you don't have to really take the implant out of the body, unlike the commonly used implants like a permanent metals like stainless steel or titanium or chromium cobalt based implant. So however, the degradation, the control of the magnesium alloys corrode very quickly. So this is a problem. So degradation control of magnesium alloys in a corrosive media like our human body fluid is a big challenge. So the material has got a potential, but still there are some challenges. How you can control the degradation of the magnesium alloys in the same rate of the healing of the body. So this is one of the challenge where it's a manufacturing challenge. How can actually manufacture implant of these particular materials that can provide specific properties like a controlled degradation. And there are another one is the fatigue life of the metallic parts. So there are a lot of metallic components, metallic parts are being used in machineries and specific the components, and where that component might be subject to some different types of loading. Kind of it could be subject to like a corrosive media, could be the impact or abrasion. And then the extending the fatigue life of those components are very critical. So this is another manufacturing challenge when you develop some metallic components for some industry. And for example, in the mining areas where you have a lot of equipments like the pump, slurry pump, and other machineries, they're made of metal components, so their fatigue life is very critical. So, and wear life extension of the extreme environment. So this is another example. The wear resistance of the component has to sustain kind of a all this extreme harsh environment over there. So increasing the bonding life of the composite laminates is another. So a lot of composite materials are being used in the industry. So and however, to increase the bonding strength of the composite is another challenge. So how can actually make the sheet of materials bonded together, and they can actually survive for a long time under the different loading conditions. So I think that these are the few examples I'm just putting up here. So we believe that these challenges could be addressed by surface engineering. So what the surface engineering means is basically you engineer the surface, the properties of the component of the material. Just giving you a bit of idea of surface manufacturing, the market growth in the world. So it's about $500 million by 2030. So any product, lot of products in the world can be innovated by surface manufacturing. So you can actually modify the surface or engineer the surface of the component, and you can actually create the component quite valuable. You can put a lot of high value into the product. So they're creating the significant market growth in the world. So it is one of the big area in the manufacturing where surface engineering has been quite critical and has been the pinpoint, I would say. Just to give you a little bit of this, I mentioned about this biodegradable magnesium implant. So we have been, my research group has been working on this particular materials for some time, and we try to apply different sort of surface engineering technique or surface engineering surface modification approaches. So, so this is just an example of the implant, like the bone implant. If you have a bone fracture in the lower limb or hand or wrist, anywhere. So generally the permanent implant, like the metal, stainless steel, or other types of permanent implant, is put into the bone, put into the body to basically restore the function of the bone for a certain period of time. And then after the bone has been healed, then implant has to be taken out from the body to some sort of surgical procedure. So, however, this particular material, we call it the biodegradable magnesium-based implant. So this implant would be made of like a magnesium alloy kind of material. So that is being degraded into the body over the time. So, however, the main problem with this material is that the faster degradation because when the material comes into the corrosive, like a salty media within our body, and then it actually degrades. So the appropriate control of the degradation is very critical to realize the potential of this particular material. So, so this is one of the areas, and I think I just briefly mentioned that, just giving you the more further details about what are the critical equipment or components that subject to some sort of extreme or harsh environment. So mining, some of the critical mining components, like you can see here slurry pump. So slurry pump is a very much complex machineries, and generally it is being used to transport the abrasive slurry of the minerals from one place to another place. So however, because of the abrasiveness of this particular minerals, the number of some critical components within the pump subject to kind of a like impact, abrasion, erosion, even the corrosion. And these are some of the components, like the throat bush, kind of a slurry pump casing, and then impellers. Also, over the time, they actually worn out, right? So the failure basically starts of the components from the surface. So because of the wear and impact of those things. So, and you can imagine that in a mining industry like in Australia, is a very serious business in Australia. So if there is a downtime because of the failure of one of the components, so there's a huge significant loss, right? So these are very serious problem in Australia. Like I think in terms of how you can actually develop or improve the service life of these components. So of course, in the aerospace industry, or the composite laminated structure is being used a lot because of their lightweightness, and also they can also absorb energy impact, and also the lightweight structure. And so what is the composite structure is made of? Generally, you can have a lattice structure in between, but you have basically two and multiple sheets are being actually stacked together and bonded to make a lightweight structure that can go into the different component into the aerospace, like for example in the aircraft. So the composite is being used not only in aircraft or aerospace engineering, but there are many other areas where the composite is growingly used. So one of the issue in the laminated composite structure is the bonding between the sheets. It could be between the metal and metal, or it could be metal and the plastic in the sheets, right? So the bonding with the adhesive, some sort of adhesive, is very critical to the integrity and the service life of that particular component. So we believe that the surface engineering also could be applied into this kind of a sheet metal or laminated structure to improve their service life as well. So so these are some of the areas where there are a lot of research going on, but there are still challenges, and innovative research work are being immersed constantly. And as part of that, we are also getting into this kind of area to really discover some of the new technologies or new process and new surface engineering techniques to improve. Okay, along this line, I think so. Okay, so before you basically do any sort of surface engineering or surface manufacturing, so of course you have to manufacture first a component, like the bulk of the component you have to manufacture. So there are two ways generally the component is being made. Either one is the conventional manufacturing process, and of course nowadays we have got additive manufacturing, which is also has been for a long time, and it is quite growing, I would say. So conventional manufacturing involves like the casting, right? Starting with the casting, and then you do the machining and other processing. And of course, you can make any part, any component by the conventional manufacturing process, but conventional manufacturing process has some limitations as well. So it is, of course, it is often the time consuming and also the costly, because you have to make quite significant the mold and the die, everything to make the casting. And so there are some benefits also. It is, you can, by casting, you generally can make very homogeneous and isotropic products. So this is pretty good. But there are some other problems with the material waste by machining. So the casted product component cannot be used immediately. So you have to do some sort of machining and other processing to get to the right geometry and tolerance, and also as well as finishing. And of course, additive manufacturing is the significantly growing now. And the good thing with additive manufacturing, it is you can design and make fabricate any complex part. So, and I guess everyone in the manufacturing arena, they're quite now excited about the additive manufacturing. So, and you can make a complex part quite fast, quite quick turnaround time. However, there are some other problem with this process, is that the properties of the materials are not isotropic. It could be anisotropic. That means the property could be different along the different directions of the material. How do you build the material? It is a green process. Of course, it is the future of the manufacturing. So, okay, so the good thing is, the main thing here, I'm going to tell that regardless of the manufacturing techniques, either conventional or additive manufacturing, so there are some, still there are some issues with each of these process. So one of the issue is basically the surface, the defects or surface defects are the prime issues. So, and then that's going to basically impact quite negatively the quality or the mechanical integrity of the final products. So that means we need to do, before we actually get to the final product, we need to do some sort of the surface modification or surface alteration, and that's what we are calling the surface manufacturing or surface engineering. So we thought if we can actually innovate the surface engineering, we can actually improve further the surface and mechanical properties of the component, and that is going to really help to extend the service life of the product as well. So when we talk about the surface engineering, so we need to look at what are the surface characteristics. What are the surface characteristics are very critical, and that can actually cause the failure, mechanical failure. So generally the kind of any sort of a failure starts from the surface imperfection, like any sort of surface defects. So what are the surface defects? So it could be, the surface could be rough because of the roughness, right? And the surface or component might have some sort of microstructure. So the microstructure could be is not favorable to specific properties, right? And the surface might be the material might have some porosity because of the nature of the manufacturing process, which is either conventional or even the additive manufacturing. So each process has got its own kind of a problem still. So porosity, often the product might have a porosity. So this could be another reasons for mechanical failure of your final product or component in the real application. So cracks, residual stress. So these are some of the surface integrity properties or surface characteristics are really going to affect the failure or of your in other words, is going to affect the performance of the component. So why the surface engineering and how we can do that? So surface engineering is nothing else, is but to really alter the surface texture or the microstructure of the material at the surface level as well as the subsurface level. For example, as you can see here, this is the cross section. You can see some of the grain of the materials, and you can see the surface is a bit rough. And then so surface engineering, so we can actually modify the surface. We can really improve the surface texture, and by doing that surface modification, we can also change the microstructure. So that means you can modify the grain alterations, and then that's going to really improve some other properties. So we can actually improve the surface finish, and you can induce some sort of work hardening because of the surface modification techniques, and and we can reduce the porosity as well. So by doing these surface alterations, so the final outcome we want to see is that basically improve the hardness of the material, because harder the material, generally it would be more wear resistant. So this is another important property. Corrosion protection. So some of the components we need to have a very highly corrosion resistance, wear resistance, and we can improve the fatigue life as well, fracture toughness, and also weightability. Some of the material needs to be more weightable, or some are not. So we can basically control the surface texture as well. That will give us the different sort of weightability or specific weightability we need for a specific component. Okay, so now the question is that what are the surface engineering approaches currently being used in the industry or in the research arena? So there are the range of surface modification or surface engineering approaches are being used here. As you can see, starting from the machining, laser pinning, and is UNSM, SMAT, and as you can see, and also the cavitation pinning and short pinning, plastic burnishing, which is kind of a roller, deep rolling, or you can use the ball or roller to really modify the surface. And also you can do the coating is another surface modification techniques. So there are a range of surface modification or alteration approaches are being used. And my research group is basically focused on one of the surface engineering technique, which is we heavily focused on the plasticity burnishing, as well as we do also some work with the short pinning as well. Machining is a very common process. It's a very generic approach, but in order to really create or induce some sort of modification into the material, so plasticity burnishing and the short pinnings are quite used now. So these are the techniques that are being used, and they're very much beneficial, but they might have also some challenges with specific to each of the techniques. So I'm going to give you a bit of a few case studies from my research group here. So one example is that I mentioned about the implant. So we generally the ball burnishing, we thought we can apply actually the ball burnishing technique, which is basically nothing else. You apply you actually apply force onto the material by a spherical ball or roller. So basically this ball actually apply the compressive stress into the material, and then plastically deform the peaks and valleys of the materials. So you can actually improve the surface finish, as well as also you create you basically modify the grain of the material. So generally you may basically make the grain from the coarse to fine to improve some of the surface properties. So, but in this particular approach, we have applied that to control the degradation of the magnesium implant. We also, after the ball burnishing, we also apply the hydroxyapatite coating. So it's a like we call it the hybrid surface engineering technique. So hybrid ball varnishing plus HA treatment. So by applying the hydroxyapatite coating, we basically create a barrier layer onto the varnish surface. So by adding this layer or coating, we actually augment further the corrosion resistance of the magnesium alloy. So by doing that, we can actually extend the degradation or delay the degradation process for some time. But we don't want the material to be not to be degraded. We want the material to be degraded, but we just want to delay the process by creating this sort of layer onto the magnesium alloys. So we have done some of the study here. We looked into the surface, untreated and varnish surface, and then we applied the coating on top of the surface, and this is the HA coating. And we also did some sort of roughness analysis. We found that, of course, by applying the coating on top of the varnish surface, surface become rough. As you can see, the coated surface looks pretty rough here. We did some hardness measurements. So after the varnishing, we like to see what is the effect of the ball varnishing, which is basically the cold hardening process. So we found that the varnished surface actually the hardness has been increased up to a certain like a 400 micrometer depth around. And then we looked into the contact angle, which is to see the weightability of the surface, because the magnesium implant has to go into the body. So bone has to really match with the implant. So surface weightability is going to help integrate the bone with the implant as well. So we found that for the modified surface has been much more weightable, has much more weightability. And we also looked into the adhesive strength between the coating and the varnished surface. So we found that the coated surface coating has got a very good strength. So that means it also gives you the better corrosion resistance as well. And we finally did the corrosion resistance to understand the degradation and the kinetics of the varnished or modified surface. We found that after the varnished surface and the varnished plus coated surface actually improved the corrosion resistance significantly. So that means the approach actually worked pretty good. And we also have recently applied the similar technique, like the ball varnishing technique, onto the laser metal deposited metal alloys. For example, this is the one of the laser cladded process. So generally, we can actually deposit the coating onto the metal components to repair. And then, however, the problem with the laser or laser metal deposited alloys is the surface is very, very rough. And also, as you can see, surface become rough. This is the one of the component after the laser cladding. And also there might be other inherent properties like the porosity and cracks. So we thought, okay, we should apply the ball varnishing treatment onto the laser cladded surface to improve its mechanical properties as well. And we did that. This is the technique. I just show you the video of the ball varnishing technique we apply. This is the sample has been set up on the table, and this is the ball varnishing tool being pressurized by the hydraulic fluid, and it modified the surface. And these are some of the results we have. You can see here after the ball varnishing, surface roughness has improved a lot, significantly, I would say. And then similarly, we also looked into the hardness improvement as well. We can see that at the top surface, the surface hardness has improved significantly, and we looked into the corrosion resistance of the material as well. And we can see here the corrosion resistance, which is basically the higher potential or less current density, means that basically the material has got a higher corrosion resistance. So this is another nice outcome of this treatment as well. Recently, we also looked into not only the mechanical properties like the hardness, corrosion resistance, and the surface roughness. We also looked into the fatigue life. So fatigue life is very, very important for the components, because most of the materials or components actually fail due to the fatigue. So we also looked into the fatigue performance of this material. So we actually prepared the fatigue specimen, like a dog bone specimen like this, and we ball varnished this tool. We ball varnish onto both surfaces of the dog bone specimen, and then we put this specimen onto the Instron universal metal testing machine, and we actually apply some sort of cyclic loading at a 10 hertz And then we looked into the number of cycles until material actually fails. And this is some of the results you can see here. So this is the SN curve of the materials, and as you can see here, untreated surface or component specimen is basically the blue one, and after the orange one is basically ball varnished treated sample. As you can see here, all the samples actually has gone over the million cycles, so that means we have done the test in a high cycle fatigue. And then we can see here that the ball varnished treated surface specimen has got a higher the fatigue life or fatigue strength. So in terms of the values here, we also looked into the fatigue strength or the fatigue ratio. We can see that the treated surface or ball varnished treated surface has got almost like 50% increase of the fatigue life as well compared to the untreated specimen. And this is more further down to the looking into the fractography of the specimen, like the failure mechanism due to the fatigue. So this is untreated specimen we looked into under the microscope, and you can see here the specimen actually start to fail from the edge of the sample. So from this is the edge of the surface, so it starts from the here, and this is very common, and then it propagates and until it's fractured, right? So, however, we found that for the treated surface, after our ball varnishing treatment, we found that the fracture actually the initiated or crack actually initiated from not from the edge of the surface, but rather somewhere inside. So, which is around 350 micron deeper. So that means after we applied the ball varnishing, we actually modify the subsurface microstructure, and that actually allows to really start crack to start a little bit from the subsurface, not from the edge of the surface. So this is another indication of the improvement of the fatigue life by the ball varnishing. Okay, so I think these are the treatments I have just shown you earlier. These are the kind of offline. So you make a sample and you do the treatment later on offline, right? However, nowadays the in situ hybrid surface treatment is growing, because especially it is very important in the case of the laser metal deposited metal alloys. So for example, you have got this is the metal deposition process you have, and then generally after the metal deposition, the grain of the microstructure grain is generally coarse. However, if you can actually add another kind of treatment tool just next to the machine onto the laser head, then you can actually modify the interlayer just next to the laser the deposition here. So by doing the in situ treatment, the cold working, you can actually modify the surface layer, each layer, in a way to improve the properties as well. So this is one of the results, as you can see. So generally this is after the metal depositions, the porosity, you can see is quite porous, but after the cold surface treatment, like a ball varnishing treatment, you can see here the porosity has been less, and also you can actually reverse the tensile stress into the compressive stress. So compressive stress is generally beneficial for the fatigue life, and as well as you can it has improved some of the engineering properties like the yield strength and then some Young's modulus, so on. So in situ hybrid surface treatment is also growing, and it is quite popular. So one of my students now is working on this in situ hybrid surface treatment. So the computational modeling is also growing to optimize the in situ or hybrid ball varnishing or surface engineering techniques. So this is just one of the examples of the in situ the surface treatment which has been done by the finite treatment modeling. So as you can see here, you can the grain was a bit coarse after the laser cladding, but next to the cladding, if you have a roller ball varnishing, you actually do the treatment next to it and instantly in situ, then you can see that you make the grain much more the kind of a fine grain, and fine grain means basically you have a better mechanical properties. And then this can be evident from this picture, as you can see here. So you can improve the mechanical properties like the yield stress, as well as you can create some the compressive stress into the subsurface as well. Along with the ball varnishing treatment, which is like a cold working, like you have a tool, you have a ball which is rolling onto the material. However, my group also recently focused on the laser treatment, which is basically, laser treatment is not to manufacture the coating, rather it is to really surface finish the surface finish the component. For example, this is the one example of the titanium alloys, which is manufactured by the additive manufacturing process. But if you can apply the laser finishing, which is basically you apply the laser energy into the surface, so make the rough surface into very smooth. So what happens here? So laser actually melt the small peaks and valleys, the drops onto the surface, and then they actually melted the melted materials is going to flow into the valleys and then make the surface very, very smooth. So we have recently done these kind of experiments on a PLA, 3D printed PLA surface, and we found that this is the as print PLA surface, and after the laser finished, we found that surface roughness has been dropped from 26 micron to the 8 micron. So there are other benefits also you can have. So improving the other mechanical properties you can achieve by doing this surface laser surface treatment as well. We also have been recently doing the laser treatment on the metal laminates, metal and metal laminates, to increase the bonding strength between the two sheets. And this is just one example of that. So we have done the we have compared the like a laser treatment as well as other commonly used treatment like the abrasion and the oxalic acid treatment. So this is the laser treated surface of the metal sheet. For example, you want to bond together with another one, and as you can see, the laser treated surface becomes very rough. So this actually rough surface is quite beneficial for bonding strength. So that means when you have the adhesives in between the two sheets, so basically adhesives can flow into these rough cavities and then actually make the very good bonding between the sheets. And we have done some testing, lab shear testing as well, to investigate the performance of the bonding, and we found that laser treated the laminate actually give us pretty much like equivalent strength, bonding strength of commonly industry practiced treatment, which is the acid treatment. So that means laser treatment is a more environment friendly as opposed to the like acid based, which is toxic. So that was the main aim, to really develop a sustainable environment friendly surface modification technique to improve the bonding strength. And we have done also some tests of the after the laser treated, and we make the bonding of the sheets, and we make the laminates. And then we also investigated the perforation resistance of the laminated sheet or metal plastic laminates with the three different types of indentor, like a conical, hemispherical, or blunt. And we found that the failure of this of the surface treated laser treated laminates showed a very regular and good performance as well. Okay, some of the emerging areas in surface manufacturing is basically, it is not about you just make do the treatment, you manufacture a component, and either by laser manufacturing or and you basically do some surface surface modifications later on. However, we can actually improve the process much better in terms of if you can basically monitor and try to, if you can understand the process better in situ. So that's why nowadays a lot of smart sensors are being deployed into around the machines to really monitor and detect some of the characteristics, process characteristics for potential improvement or optimization. So that means when you have got this sort of like you have a camera, you can have the different sensor, laser sensor to detect, or pyrometer to detect the temperature, and other even the ultrasonic sensor to detect some of the failure, like for example crack failures during the laser cladding as well. So a lot of smart sensors are being used into the industry to detect for example the laser metal deposition process. So because if you know the more information about the process, then you have a better understanding how to basically optimize the process and how you can actually get the better final product. So that's the main reason of doing that. And while you have a lot of sensors are being involved, so then it's coming down to the taking the advantage of the Industry 4. Like one of the speaker, I guess, yesterday was talking about the Collins Aerospace presenter talking about the Industry 4 revolution. So I think that this is exactly can be also applied into the surface manufacturing area as well. So, and is being used now. So basically, if you can, the Industry 4 is nothing else but basically utilizing all this digital capability. So you make the whole industry, physical industry, into the digital format, and process, equipment, machines, everything, and then you basically see the whole process, and you can monitor the performance of the whole process just in front of the computer. And so there are a lot of benefits of doing that. Of course, you can monitor easily from anywhere, right? And it will give you the better process control. Like you can have more information of the process and product, so you'll have a ability to really control for potential improvements. So you can develop the new type of materials and new type of alloys, and also to help for quality control as well. And I think so in the case of the surface manufacturing, like surface modification techniques, laser metal deposition, so Industry 4 is also another big the trust, creating big trust to really improve the whole process. And along with the Industry 4 or digital transformation of the industry, the machine learning or artificial intelligence is being playing a key role to further really give another level of improvement. So that means what that means. So once you collect all this data information through all these sensors like IoT, through the real time. So, and of course, it is not enough to get the data. So, but we need to really process and analyze the data, and really where basically the machine learning or data analytics is going to really give the operators or the companies really kind of insight what the data means for them from the business perspective. So I guess the machine learning, which is a kind of another kind of artificial intelligence, and together with the data analytics tool, will create another kind of a improve the sustainable productivity and the resource management for surface engineering areas. Yeah, so I guess that's pretty much the end of my talk. So I'm just like to finish with a summary notes here. So what I'm going to trying to say today is that the surface manufacturing, or you can say surface engineering of a material or component, is very critical, and it is at the heart of the economic growth of any country, really for the growth of the manufacturing. So manufacturing is growing, that the country is growing. So opportunity for the surface manufacturing for product development is enormous. So there are different ways you can actually apply the surface engineering to improve your product, to improve the service life of the component, right? So I just have given you a few examples of the areas. There are plenty of other areas where manufacturing or surface manufacturing can be applied to improve the productivity. So surface engineering could enable develop or improve the critical products with the tailored properties. So tailored properties means you can actually manufacture a component or part with the specific properties needed for that particular applications. The technique can dramatically increase the service life and the productivity. And the surface engineered products and the solutions will create niche market. I mentioned this at the beginning of my talk. So that means if you can come up with the innovative surface manufacturing technique, that means you create the new type of product. So disruptive product, niche market, and that is competitive for your business. And and furthermore, with artificial intelligence together with like IoT and also like Industry 4, and smart surface manufacturing or surface engineering will revolutionize the future manufacturing landscape. So yeah, so that's my talk. And then I just like to acknowledge the funding bodies. where they who actually supported my research through both in-kind and cash contributions, and also my industry partners as well. So these are the number of industry partners we have worked closely with and addressed some of their problems. And yeah, thank you.
Thank you, sir. We are truly grateful. Despite of your busy schedule, you agreed to share your expertise and latest research with us. Thank you once again for your valuable insights on emerging trends, opportunities, and technology pathways related to surface engineering. Your talk definitely add value to scientific and academic fraternity. Thank you, sir.
So, thank you. Thank you very much.
Sir, there are a couple of questions from audience side.
Yep.
So, good evening, sir.
Yep.
Sir, this is a question related with fatigue.
Yep.
Yeah, I have seen two graphs. One is dealing with stress amplitude and failure, number of cycles. So another one is, it's talk about the fatigue strength. So what is the difference between these two? Fatigue strength and the stress amplitude.
Okay. Okay. So fatigue strength, we actually calculated the fatigue strength at a, let's say, generally it is considered, let's say, if your the material or part doesn't fail, goes up to like a 1 million cycle, it passed 1 million cycle and it didn't fail. So that means you have reached pretty much the endurance limit, endurance limit of that particular material. So what we have, fatigue strength we have calculated. We have, let's say, at a 1 million cycle of cycle, and we calculated the strength, like a stress of the untreated specimen, and also at the same 1 million cycle we also look at the stress of the failure stress of the treated specimen. So we actually then calculated the ratio between that. So that is what we call the fatigue strength.
Big test. Hello, sir.
Yep.
Yeah. This stress amplitude. So that will give the different value.
The stress amplitude is yeah, I think that we looked for at a 1 million cycle. We compared the kind of a stress amplitude of both the specimen, and this is how we calculated the kind of a fatigue strength. Yes. So I think that you can compare the results as a fatigue strength. Some people actually compare also as a number of cycle. So the sample actually has gone like this number of cycle or not. So there are different ways you can actually present. You can talk about you can compare the fatigue performance of the materials.
Yeah. Okay. So the fatigue strength, which leads to the endurance strength of that particular material. We can say, yeah, the endurance strength is related with this fatigue strength graph.
That's right. Yeah, that's right. Yeah. So that is we compare the strength of the material at a endurance limit of the both materials. Yeah.
Oh, thank you, sir.
Hello, sir. Very informative talk. I have a few queries. One query is, sir, being an aerospace laboratory worker, I am doing EBC coating and TBC coating, environmental barrier coating and thermal barrier coating for aerospace applications. So what is the best way to make uniform thickness, sir? Because we are doing the coating for higher temperature application. So there is one small issue is uniform coating is not coming. What is the best technique to maintain the uniform thickness?
Okay, so just to understand, you are saying that you are creating some coating for aerospace components. So what kind of coating and what is the technique you use for coating?
Sir, usually we are prefer slurry spray coating, thermal spray
Slurry-
coating.
Thermal spray coating. Okay. Okay, so it is a high temperature the coating process, thermal spray coating. So I think the thermal spray coating is quite. There are a number of factors I think that maybe you should look at. We have recently started work with industry partner, and they also have been doing thermal spray coating like a HBOF, right? HBOF kind of a coating. So I guess it depends on the mixture of like your particles and the speed of the particles or jet, and also the temperature and all these things really, and also I guess the distance between the your substrate and the like kind of your jet nozzle. Could be I think the mixture and the temperature composition would be the critical as well to really get the uniform thickness. So I think that there are a number of factors. Generally, the industry also have a bit difficulty to get the really uniform thickness of coating on a substrate. So did you try to really change the different parameters?
Excuse me, sir.
Sir. What, sir?
Yeah, I mean, did you? What kind of parameters you have changed to really see the which actually work for you or not? So did you try the different the temperature or different the powder velocity, the kinetic energy of the powders?
Slurry so, that loading we have changed, the solution we have changed, and condition parameter also we have changed temperature.
Okay, so it is I think the slurry condition,
Yes, sir.
the powder or slurry condition is very very important. Maybe I'm not sure that and also the speed, like the what is speed or what kinetic energy you basically throw the slurry into the substrate. Did you control the also speed as well or energy?
Okay, sir. And how we should take care of the thermal coefficient, thermal expansion coefficient? Because substrate
of the
and
coating.
whatever coating, the thermal expansion should be matched.
Yeah.
So how we should take care about this important parameter?
Maybe that's a good question. I guess one way you can really control the thermal expansion or match, perhaps you can. Did you also preheat the surface? Preheat the substrate?
Preheat the substrate.
Okay, yeah. So because when you actually throw the slurry into the substrate, definitely it is hot, right? Hot slurry, and then it impact into the surface, right? Substrate, and then of course there is a temperature gradient, right? So if you can reduce the temperature gradient between the coating material, the slurry and the substrate material, perhaps you can actually reduce the thermal coefficient, thermal expansion.
Okay, sir. Okay, sir. Thank you, sir.
Any more question? Thank you, sir. Thank you, sir, for your valuable insights on surface engineering and its application. So now we are moving to the end of the session, end of this conference, that is the validatory session. So may I request Dr. Abhiyam Giris, HOD Mechanical, to come on the dais, and also my colleague convener, Dr. Hemant Mohit Kumar, to take his seat. On behalf of the organizing team, ICAMAE 2023, I, Dr. Sashmita Val, along with my colleague, Dr. Mohit Hemant Kumar, conveners of the conference, take pleasure welcoming you all to today's valedictory session. Distinguished guests, respected management, fellow students and staff, delegates, ladies and gentlemen. It is an honor to stand before you today to deliver the valedictory remarks as we come to the close of our first joint international conference on advances in mechanical and aerospace engineering, ARTCON 2 series, ICAMAE 2023. The conference is jointly organized by Alliance University and the University of Strathclyde, Glasgow, UK. Over the past 2 days, we have engaged in meaningful dialogue, shared innovative ideas, and formed new connections, all aimed at furthering research, increasing collaboration, and driving progress in our field. There were 310 full manuscripts received. Out of those, 116 papers were finalized for presentation at the conference. We received papers from around 25 countries around the world, like Austria, Thailand, the Netherlands, US, China, Oman, Nigeria, etc. There were 116 papers belong to 5 tracks such as material science, production engineering, design engineering, fluid and thermal, aerospace engineering, was presented by research scholars, faculties, and students in 5 parallel sessions conducted on both 28th and 29th November 2023. There were 2 keynote speeches. On the first day, that is 28th November, we had a keynote speech by Mr. Satyaswarup Panda, Director, Collins Aerospace, about the recent advances in mechanical and aerospace aligned with the conference theme. We are truly grateful, sir, that despite of your busy schedule, you agreed to share your expertise and latest research with us. It introduced fresh ideas and gave conference participants lots to think about regarding developments and new directions in materials and sustainability. On the second day of the conference, we had a keynote address by Dr. Mohammad Uddin, Associate Professor at the University of South Australia. In his talk, he emphasized the growing relevance and opportunities for the surface engineering field to enable advanced material solution across industry. Thank you, sir, for your valuable insights on emerging trends, opportunities, and technologies related to surface engineering. We will also have an industry visit to Balboline, Bengaluru for all conference delegates tomorrow, that is 30th November. Before we conclude this remarkable event, it is both a pleasure and a privilege to take a moment to express our profound gratitude to all individuals whose tireless efforts have been the heartbeat of this conference, ICAMAE 2023. First and foremost, I would like to extend my heartfelt thanks to the management for their visionary leadership and unwavering support in organizing this exceptional conference. Your commitment to academic excellence and the pursuit of knowledge has laid the foundation for the success of ICAMAE 2023. Also, a sincere thanks to our Honorable Pro-Chancellor, Mr. Abhay Chebi, and Pro-Vice-Chancellor Academics, B. Priestley San, for their unwavering commitment to academic excellence and their constant encouragement. My sincere gratitude to our Dean, Dr. Riba Kora, for her visionary leadership and wholehearted support that made this conference possible. Madam, your encouragement of international collaboration and emphasis on staying updated with the latest research has motivated several faculty-led student delegations from our institutions to actively participate and engage with peers from across the world this past 2 days. I would like to express my deepest gratitude to the head of Department, Mechanical, Dr. B.M. Giris, Alliance University, for his support and guidance. Dear Sir, your leadership has been instrumental in ensuring the success of this grand conference ICAMAE 2023. I am grateful to the leadership team at University of Strathclyde, Glasgow, for joining hands with us in envisioning, planning, and executing this impactful event. From the initial brainstorming to shaping a stimulating program covering diverse research areas, their partnership has been invaluable. I wish to express my heartfelt thanks to Dr. Thanasius Tampes, Faculty Mechanical and Aerospace Engineering at the University of Strathclyde, Glasgow for this. This conference would not have attained such resounding success without your leadership as an able collaborator. A special mention to our branding team, whose creativity has brought ICAMAE 2023 to life. Your efforts in crafting an identity for this conference have not only enhanced its visibility, but have also left an indelible mark on the memories of all those who attended. From the local arrangements to program development to coordinating speakers and guests, it took careful planning and dedication to bring us together under one roof. I would like to express my deepest appreciation to our conference organizers, colleagues, lab technicians, mechanical and aerospace, facility, ITS and transport, purchase, CAN office, who worked tirelessly behind the scenes to make this event possible. Thank you for providing us this platform to come together as a community. Thank you, dear student volunteers, for being the unsung heroes of ICAMAE 2023. Your efforts have been invaluable and your impact will undoubtedly resonate long after the curtains fall on this extraordinary event. I also wish to thank all the presenters, researchers, scholars, and student delegates who joined from various parts of the world, online and offline, to actively participate in this conference. We are grateful that you took time out of your busy schedule to share the findings from your important work, which will undoubtedly resonate beyond the walls of this venue. In conclusion, as we bid farewell to ICAMAE 2023, let us carry forward the spirit of collaboration, innovation, and scholarly pursuit that has defined this conference. May the relationship have formed and the knowledge shared serve as catalyst for future reference. We have received the final scores of papers from all reviewers and session chairs. Based on that, shortly we will be announcing Best Oral Presentation and Most Impactful Technology or Innovation Award on the conference website. Kindly visit the website for updates. Thank you all for being a part of this incredible journey. Thank you. Feedback form will be shared to all the participants through mail and WhatsApp also. Kindly fill it up and send it back to us. Your feedback is very valuable for us. So kindly do it. Thank you. I want some feedback from the collaborators and the delegates who are present in this venue. Sir, if you want. Yes, sir. You can come here.
So good afternoon to all. This is Dr. Ronald, Assistant Professor, Department of Mechanical Engineering, NIT Puducherry, which is in Karaikal. So I would like to express my sincere thanks to the organizer, especially the conveners, Dr. Mohit and Dr. Sashmita ma'am, and head of the department and the management for providing such a nice opportunity. So after 2-3 years, I think after COVID, this is personally my first in-person conference, which I was attended. And especially the arrangement is very nice. The hospitality, the food, everything is fine. I appreciate the organizers. They have to conduct more conferences, especially in this series of ICAMAE, AdCon. So hopefully I will be expecting AdCon 3 very soon. And personally, I thank Dr. Mohit. He was my junior in NIT Trichy. I have not seen him, but I have seen his profile in Google Scholar. So he's a good researcher. He's a multi-talented guy who have some administrative research as well as teaching capability. Thank you. Thank you for this opportunity.
Myself, I'm working as a technical officer in a National Aerospace Laboratory. It was very nice experience since yesterday. I don't know how today I spent here. And when it comes to interaction, Dr. Mohit and Dr. Madam is very active, and their interaction is very good for us. And presentation also is went well. And very beautiful campus with beautiful organization committee. Just wow. And my suggestion is strength is little bit people like as a student, you people, you have to show the interest for conference, because this is the stage you can share your ideas, you can get it your things, and at least you can get it your same domain people, some aerospace domain people, some in mechanical industry people, as a R&D people, you can interact me. So you should meet the people and interact with them and get the opportunity for your internship and all. It will be good for us. And if you need any internship from our NL side, National Aerospace Laboratory, so NL, it is providing for BTech student 2 months internship. So who are interested, you can contact me. We are ready for help. And thanks for this opportunity. And we'll hope we'll meet Alliance University soon. Thank you.
Thank you, delegates, for sharing your valuable feedback. Now I am going to close the session. Thank you all once again. I hope very soon we'll be meeting at CON 3. Thank you.